Imagine a symphony where every instrument has to play its part in perfect harmony to create a beautiful melody. In our bodies, that orchestra is made up of neurons, and the electrical signals they generate are the notes that keep us functioning. Today, we'll explore how these signals travel and how neurons communicate with one another to create the music of life. Neurons, the rock stars of the nervous system, are made up of three main parts. First, we have the dendrites. Think of them as the antennae, picking up signals from other neurons. Then there's the soma, or cell body, which houses the nucleus and all the neurons' organelles. Finally, we have the axon, the neuron's personal highway, which is wrapped in a fatty layer called myelin, much like insulation on a wire, allowing signals to travel faster. Imagine the dendrites as tiny ears listening for chemical whispers from neighboring neurons. When a neurotransmitter binds to a receptor on a dendrite, it's like flipping a switch that opens ion channels. These channels let charged ions flow in and out of the cell, transforming that chemical whisper into an electrical shout. This change in charge can eventually trigger an action potential, a rapid electrical signal that races down the axon. Before a neuron fires, it's in a resting state, like a calm lake. At this point, the cell has a negative charge of about 65 millivolts, called the resting membrane potential. This charge is due to a higher concentration of sodium, Na+, chloride, Cla, and calcium, Ca2+, ions outside the cell, and more potassium, K+, and negatively charged anions, Ae, inside the cell. This balance creates the perfect setup for a powerful wave of electrical activity when the neuron decides to fire. Neurons are like scales, constantly balancing excitatory and inhibitory inputs. When a neurotransmitter binds to a receptor, it opens ligand-gated ion channels. If sodium, Na+, flows in, it adds a positive charge, pushing the neuron toward an action potential. That's an excitatory postsynaptic potential, EPSP. On the other hand, if chloride, Cl, flows in, it adds a negative charge, pulling the neuron away from firing. That's an inhibitory postsynaptic potential, IPSP. If enough EPSPs build up, they push the neuron's charge to a critical threshold, usually around 55 millivolts. It's like adding just enough fuel to ignite a fire. When this threshold is reached, voltage-gated sodium channels at the axon hillock open and sodium ions flood into the neuron, triggering the action potential, the neuron's way of saying, "It's go time." As sodium ions rush into the cell, the neuron's charge swings from negative to positive, reaching up to +40 millivolts. This depolarization wave travels down the axon like dominoes falling one by one. Each voltage-gated sodium channel opens in sequence, creating a chain reaction that sends the signal racing along at speeds up to 100 meters per second. But this electrical party doesn't last forever. Sodium channels have an inactivation gate that slams shut, stopping the flow of sodium ions. At the same time, slower potassium channels finally open, letting potassium, K+ ions flow out of the cell, restoring the negative charge. This process, called repolarization, helps reset the neuron back to its resting state. During repolarization, the neuron enters its absolute refractory period, meaning it's completely unresponsive to any new signals, like taking a mandatory timeout. This ensures that action potentials don't overlap or travel backward. As potassium continues to flow out, the cell briefly becomes more negative than usual. This is called hyperpolarization. The neuron then enters the relative refractory period, where it's possible, but much harder, to trigger another action potential. To fully reset, the neuron relies on the sodium-potassium pump, an active transporter that moves 3 sodium ions out of the cell and 2 potassium ions in. This pump is the neuron's janitor, cleaning up after all that excitement and preparing the cell for the next signal. Remember that fatty myelin wrapping around the axon? It's not just for looks. It speeds up the action potential through a process called saltatory conduction. The signal doesn't just crawl down the axon. It leaps from one gap in the myelin, known as the node of Ranvier, to the next, like a frog hopping across lily pads. This allows the signal to travel up to 100 times faster than it would without myelin. In summary, neurons communicate using a combination of chemical signals and electrical impulses. The action potential starts with excitatory signals at the dendrites, races down the axon, and is accelerated by myelin. This complex dance of ions creates the electrical symphony that drives every thought, movement, and sensation. Make sure to check out more content from King of the Curve, and don't forget to subscribe, like, and hit that notification bell to stay updated. Thanks for joining me, and I'll see you in the next video.